Stereochemical aspects of nucleophilic substitution reaction we are going to take. First, we will define what is plane polarized light. The light whose vibrations are confined to one plane only is called plane polarized light. Question is how to get plane polarized light. When monochromatic light having single color, for example from sodium vapor lamp, is passed through a special type of prism called Nicol prism, we get plane polarized light. Now, what is optical activity? When plane polarized light is passed through any solution of organic compound, it rotates the plane polarized light either towards left or towards right. We say the organic compound is optical activity. And this property of organic compound is called optical activity. If the given compound, organic compound, rotates the plane polarized light towards right, we call it dextrorotatory. And if it rotates towards left, it is called levorotatory. And the angle through which plane polarized light is rotated is called optical rotation or specific rotation when concentration of solution is 1 gram per ml and it is used for D line of sodium vapor lamp at room temperature 298 Kelvin. So we call it specific rotation. Optical rotation becomes specific rotation. Now, what are the conditions that the given compound will show optical activity or not? First condition is molecular asymmetry. That is, there should not be any plane of symmetry, center of symmetry. No symmetry element should be present in the compound. That is, a carbon should be chiral. Chiral means one carbon should be attached to 4 different groups. And if the molecule is asymmetric, then it is called chiral molecule and it will show optical activity. Enantiomers are optical isomers which are non-superimposable mirror images of each other. And enantiomers will definitely contain chiral carbon atom. Also, the molecule will also be chiral, no plane of symmetry. Let's take up example of chirality. Your two hands are mirror images of each other, but they are non-superimposable. And there is no plane of symmetry. There is no plane of symmetry through which you can cut your hand into 2 equal halves. It means it is chiral object. Same way your foot are also chiral objects. So chiral objects are non-superimposable but mirror images of each other, and that is the specification of enantiomers. Here we have got mirror images of each other, but they are non-chiral objects, symmetrical objects, and they are superimposable mirror images, so they do not show optical isomerism. Next we are taking an example. This is the first compound denoted by A. The one carbon is attached to methyl group, another methyl group, hydrogen and OH. That is, this compound does not contain chiral carbon atom because it does not have 4 different groups. So this compound cannot show optical activity. This methyl group and this methyl group are same, due to which it does not show optical activity. Same is here. Here we have got methyl group, here we have got methyl group, both the groups are same. So it cannot show optical activity, and if we rotate this compound by 180 degree and superimpose over A, C obtained by rotating B by 180 degree, and if you observe carefully, A and C are superimposable mirror images. It means they will not show optical activity. Next we are taking example of chiral molecule. Here carbon is attached to OH, hydrogen, methyl group and ethyl group. So this compound is chiral. D is chiral. It contains chiral carbon atom, so it is chiral compound. Now what we are doing is we are writing the mirror image of this compound. So E is the mirror image of D. And if you rotate it through 180 degree, you will find that it cannot superimpose over D, which shows that mirror images are non-superimposable, therefore they are optical isomers. If one of them is dextrorotatory, other will be levorotatory. And these non-superimposable mirror images of each other are called enantiomers. Next we are taking what is meant by retention of configuration. It means the dextrorotatory substance will remain dextro. Here X is being replaced by Y, but it is in the same direction. Therefore dextro will remain dextro, levo will remain revo. It is called retention of stereochemical chemistry or stereochemical inversion is not taking place, it is stereochemical retention is taking place. The configuration or dextrorotatory substance remains as dextro, levo remains as levo. In this example, we are taking 2-methyl-butane 1-all. When reacts with HCl, water is removed and Cl will come in the same side as there was alcohol. So we get levorotatory substance we were having alcohol, and the product formed is also levorotatory 1-chloro-2-methyl-butane. So levorotatory 2-methyl-butane 1-all gives us 1-chloro-2-methyl-butane, which is also levorotatory. So this is the example of retention of configuration. Next, we are taking inversion, retention, and racemization. Let's try to see the difference. This is a chiral substance. Here we are treating it with Y, which is replacing X. It is attacking from the opposite side. So here inversion is taking place. Here Y is attacking from the same side as X. So here retention is taking place. And this side we will get both B and A, that is retention as well as inversion, both are taking place, which will lead to racemization. So here this side inversion is taking place, this side retention is taking place, and here racemization is taking place because we get equal amount of dextro and levorotatory substance. Next, we are taking the example of this. For example, we have got minus, that is levorotatory 2-bromooctane treating with nucleophile, and we get dextrorotatory octane 2-all. So levo changes to dextro, it means optical inversion or stereochemical inversion or Walden inversion is taking place. Now, how this mechanism is being followed, let's say take the formation of carbocation, it will have Sn1 mechanism. This is optically active substance, and tertiary, the secondary halide break down to form carbocation plus bromide ion will be formed. Now this carbocation which is formed, OH ion will have equal probability of attacking it from either of the side, so it will form theoretically equal amount of dextrorotatory substance and levorotatory substance, which leads to formation of racemic mixture. Practically retention is slightly more than the inversion. In general, racemization will take place. Let's take up difference between Sn1 and Sn2 mechanism, which is very important topic. First is Sn1 mechanism follows first order kinetics, that the rate of reaction depends upon only concentration of alkyl halide. Sn2 mechanism means second order kinetics, that is rate of reaction depends upon concentration of both nucleophile as well as alkyl halide, and it is a single step mechanism. Here it is two-step mechanism, and first step is the slow step, which is rate determining step and involves only tertiary halide. That's why it is first order kinetics. In Sn1 mechanism, both backside and front side attack of the nucleophile takes place, and backside attack predominates. Exclusive backside attacks of the nucleophile takes place, and this result in the formation of inversion or optical inversion takes place. Here partial racemization occurs where possible. 100% racemization practically will not be possible, but partial racemization take place. Here complete stereochemical inversion will take place, that is dextro will change to levo, levo will change to dextro. Here electronic factors influence the reaction rates largely. Here electronic factors don't play the role because electronic factors stabilize the carbocation, and this mechanism involves formation of carbocation. Here steric hindrance and not electronic factors influence the rate of reaction, because if there is steric hindrance, nucleophile will not be able to attack by Sn2 mechanism. Carbocation involves frequent rearrangement because of stability of carbocation. Primary will change to secondary, secondary will change to tertiary if possible. Here rearrangement is not possible because no carbocation is formed. Elimination is an important site reactions because tertiary halides undergo elimination reaction more readily. Here elimination is not possible because primary halides do not undergo elimination reaction easily. Next, benzyl allyl will have highest reactivity because their carbocation is stabilized by resonance. Tertiary carbocation is stabilized by hyperconjugation as well as inductive fact. Secondary carbocation is stabilized by positive inductive fact. Primary will be stabilized by primary positive inductive fact. Methyl group will be least stabilized. That is why this is the order of reactivity. Here order of reactivity is opposite. Methyl halide will be most reactive, allyl and benzyl will be least reactive. Here tertiary alkyl halide are the common substrate because they can easily form tertiary carbocation, which is stabilized by inductive effect and hyperconjugation. Here primary alkyl halide are the common substrate because they do not offer steric hindrance or they offer least steric hindrance. Here mild nucleophile can carry out the reaction like alcohols, water can favor it. Here strong nucleophiles are required for Sn2 mechanism because it has to attack the carbon from the rear side and also overcome the steric repulsion if there is any. This is favored by low concentration of nucleophilic reagent because carbocation is formed which can easily attack by low concentration of nucleophile. And this planar, there is no obstruction. It is favored by high concentration of the nucleophilic reagent because it has to find the way, means to attack the carbon atom. Solvents of high polarity will stabilize the carbocation and will favor Sn1 mechanism. Solvents of low polarity will favor it because there is no carbocation formed.